Hello, my name is Nelson Fernandes, and I recently graduated from Niles North High School in Skokie, Illinois, where I've completed my third year in our research course. I will continue my education at Southern Illinois University in Carbondale, where I will major in mechanical engineering, specialize in energy engineering. During this last year, under the mentorship of Dr. Kanchi Mandal of SIU, I conducted research on a way to create a fuel source of oxygen while reducing pollution. My project is dope Ceria as a thermochemical reaction medium for generating syngas and oxygen. First and foremost, I will explain the most crucial factor of my project, doping. This is a process of adding imperfections. The solid is known then as doubly doped. Cerium oxide, also known as Ceria, is a rare earth element with a 4+ oxidation state, which is the number of electrons in the reaction shared by atoms, and it has high oxygen ion conductivity, which means that oxygen atoms move easily. When doped, it is easily able to obtain a 3+ state where an oxygen vacancy is opened, as seen in the image below. This is a Ceria lattice that is doubly doped with zirconium oxide and yttrium nitrate. Currently, due to the doping, 2 oxygen vacancies occur. Doubly doped Ceria membranes increases its high oxygen capacity as well as its high oxygen uptake. The purpose of my project is to test the reduction-oxidation reaction, known as a redox reaction, and the conductivity of different doubly doped Ceria membranes. The control sample has Ceria doped with zirconium in 4 trials with one of the following second dopants: iron, copper, yttrium, manganese. The 2 main questions we are trying to answer examine which membrane is the best to extract oxygen from carbon dioxide, which is determined by the amount of oxygen before testing and after the carbon dioxide oxidizes. The second examines which membrane is the best to separate oxygen from air, which is determined by the amount of oxygen before testing and after the recalcination when it reacts with air. As a result, our independent variable is the doped Ceria membrane. The dependent variable are the moles of oxygen after each stage, as well as the conductivity at high temperatures, which will be explained in the conclusion. We are controlling the chemical quantities of each membrane to have each membrane of 1.5 grams, having both doped, being 7% of the total molar mass in the gases during the redox reaction. The procedure's first 6 steps is the membrane synthesis, which is a lengthy process. First, the hydrothermal processing had Ceria and the dopants magnetically stirred in deionized water. We then added SDS, which stands for sodium decasyl sulfate. This is an anionic surfactant for obtaining homogeneity in the material size and reduces surface tension. We then heated the solution to 90 degrees Celsius and added HMTA, which is an abbreviation for hexamethylene tetramine, which is a precipitating agent used to aid the binding and growth of the material. We finished heating for an hour, cooled overnight, filtered with Buckner funnels, safely cleaned by evaporating the remaining aqueous solution and deposited the semi-solid remaining to a hazardous waste company. Dried the material caught by the filter paper calcined to 700 degrees for 6 hours and synthesized into green pellets, which are uncensored membranes. Now, the membranes were ready for testing, and we used this apparatus. We used 3 gases: nitrogen, methane, and carbon dioxide. Nitrogen was used to create a constant atmosphere in the metal pipes, which ran through a furnace box and connected to a cold trap and gas chromatography, which sent the data to the computer. The membrane can also be called the oxygen carrier. We first measured the initial oxygen in the membrane, then passed methane through the pipe for 2 hours. This reduced the membrane as oxygen bonded to the carbon and broke the methane into syngas, which is a combination of carbon monoxide and hydrogen. We then passed carbon dioxide through the pipe for 2 hours, which oxidized the membrane as it produced carbon monoxide and oxygen. As you can see on this bar graph, we have the control, iron, copper, yttrium, and manganese doubly doped membranes. The blue bar is the initial oxygen in moles, the orange is after methane paste, the gray is after carbon dioxide passed, the yellow is after the membrane was recalcinated. The general trend has the methane reduce the moles of oxygen, while carbon dioxide in recalcination increases the number of moles. The table to the right are the raw numbers of the bar graph, as well as the yttrium trial and a minute-to-minute analysis of the reduction in oxidation stage. Of course, the membrane was first reduced, then oxidized, but it shows how there is a greater reduction than oxidation on the graph, and it shows in the bar graphs as more moles were removed than gained. At the bottom are the moles of oxygen and change in percent of error, change in percent between stages of the testing. Before I conclude my analysis, I want to state that there were a few minor sources of error. When heating, aluminum was used to cover the flask, which bettered the precipitation. The doping could have been better secured. The oven used to heat only had measurement every 12.5 degrees Celsius, starting at 75 degrees Celsius, so heating temperature was not precise. X-ray diffraction was used to verify the doping in the membranes. We doped the membranes to 8.9%, however, due to it being not a perfect process, we assumed it to be 7% dope, or 1 doped atom for every 12 cerium atoms. But most importantly, all the chemical measurements were within 1% of the calculated value, except for the iron nitrate in the iron dope membrane, which was 1.38%. The chemical measurements and X-ray diffractions can be found on figures 30, 40, 42 in the written report. My hypothesis asked 2 questions to determine the best membranes. The first examined the amount of oxygen gained after the carbon dioxide oxidation compared to after the methane reduction. The second examined the amount of oxygen after recalcination compared to the initial state. I determined based on the data that copper is the best to extract oxygen as it recovered 29.3% of the original oxygen between the reduction and oxidation. As you can see, copper reduced the moles the greatest and gained the most. In addition, iron was the best to separate oxygen from air as it gained 1.22% of the initial oxygen. The scattered plot graph shows the conductivity versus temperature of the control, iron, and yttrium trials. Iron is significantly exponential compared to the other trials tested, which is an indirect measurement of the ionic transport property. In conclusion, iron and copper doubly doped cerium membranes are the best to increase its overall oxygen and recover oxygen respectively. Now, with the data and findings, I can further my research by testing a triply doped cerium membrane with iron, copper, zirconium in the cerium membrane to test how the properties affect the redox reaction. So why is this research relevant? Mars' atmosphere is 95.32% carbon dioxide. One way to use the doped cerium membranes is with Martian biodomes. Biodomes are stable environments that can be built in unstable environments. As you can see in the drawing, this is an example where we have the membrane between the outer and inner wall as we pass the atmosphere through a pipe which will pass through the membrane, causing oxygen and carbon monoxide to separate. We can have the oxygen flow into the biodome while carbon monoxide elsewhere. Of course, this is a conceptual example and by no means a final product. Another example is incorporating the membranes in manufacturing plants, car exhaust, and fuel cells. The next step would to test a cerium membrane doped with zirconium as well as iron and copper, where each are doped to 7% in order to determine their individual properties, as well as second dopants occur as well if they are third dopants. There are many possibilities to use this doubly doped cerium membrane as well as possible 3 doped cerium membranes as research continues. Thank you.